check out XZF4. XZF4 steric number would be half of 8 plus 2. So which makes it 5 sp3d. sp3d, but out of 5 connections we have only 2 atoms present. Hence, it must be a trigonal bipyramidal form like this, right? Like this. And fluorine must be placed on the axial direction, which makes the lone pair to be placed on the equatorial direction like this. So lone pair must be here. So overall shape would look like a linear form. So this is a linear shape, but geometry wise, if you notice, it is trigonal bipyramid. Next, XZF4. H is half into 8 plus 4, 12, which is 6. That makes it sp3d, sp3d2. Again, 6 orbitals, but only 4 connections, which makes xenon. If at all I have to make 6 bonds, so it specifically has to be this way. 4 I can keep equatorially, and 2 I can keep it axially. So that converts into a square plane, simply a square plane here. So the shape wise, it is a square plane. Okay, so shape is square plane, square planar. Geometry which is expected was octahedral. Now in these two, if you notice something, the number of lone pairs, this has been a very standard JEE question, that number of lone pairs on xenon is 3 and bond pairs are 2. But this is on xenon. Okay. Now a lot of students get confused here. In JEE, if the question is asked very specifically to xenon, then you will answer the lone pairs as 3. But if the number of lone pairs only has been asked, okay, just the number of lone pairs, then you need to count the lone pairs present on fluorine also. So every fluorine will have 3 lone pairs. So we have two fluorines. So 3 into 2 fluorines plus another 3 on xenon. So total 9 lone pairs are present in the system or in the structure. Got it? Similarly here also, lone pairs on xenon. Only on xenon, how many we have? 2 lone pairs. Okay, bond pairs are 4. Next is XZF6. XZF6, if you see this steric number, it is half of 8 plus 6. So that makes it 7, which is sp3d3. See, sp3d3, we usually expect it as pentagonal, like this, pentagonal, then bipyramidal, like this, a bipyramid. But unfortunately, because of one lone pair present, have you noticed that there are 7 connections, I mean 7 orbitals, but there are only 6 connections, which suggests that the number of lone pair present on xenon is 1 and bond pairs are 6. In such case, instead of adapting to a pentagonal bipyramidal, it will still go for an octahedral form like this. It will go for an octahedral form. If you may remember, I discussed this in VSCPR theory. Okay, this is the octahedral form. And the lone pair will be always coming out of the one of the faces always. Any one of the face like this. This is the face of an octahedral. So through that face, lone pair will keep popping out. So like this, the lone pair will keep popping out. Okay, so that makes it the shape would be distorted octahedral. Distorted octahedral. While the geometry will be pentagonal bipyramidal. This is expected geometry. Okay, expected geometry is pentagonal bipyramidal, but the shape is distorted octahedral. Please make a note of the first three cases. See the next cases. Next one, XZ04, steric number half of 8 plus 4. So that is 6, which makes it sp3d2. And if you notice the number of bond pairs, out of 6, there are 5 molecules here. So 5 connections can be established. So 5 bond pairs, and uh, lone pairs would be lone pairs would be 1. Okay, 1 second. Right. So see, number of bond pairs are 5, lone pairs are 1 here, as per this, as per the hybridization's information. It's supposed to be an octahedral form. So that means Xz, we have 4 like this, and then double bond O. Okay, fluorine, 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 and then lone pair here, like this. One of them will cover lone pair. Okay. Right. So
Sir,
you
is
would
it
notice that
necessary that the lone pair has to come downwards only?
not necessary, because it is an octahedral form. Wherever you place it, it is exactly same only. Got it? So, for example, if you are keeping it here like this, let's say here you kept it, and you kept the lone pair here like this, okay, and double bond O here. So, isn't it the same thing, same structure as above here? This structure and that structure is same only. Okay? So, you can keep it in any place. For octahedral cases, Bent's rule is not applicable. Okay. So you will get this. Now shape wise, if you notice, it is as if there is an octahedron here like this. And on the octahedron, only one side of the face is being occupied. So other side, there is no atom. In that case, it looks like a square, which is becoming a pyramid. So shape is square pyramidal. So it is square pyramidal. Okay. And the double bond you can assess, right, beta? What is kind of a double bond it is? Because all P are occupied, S is completely saturated, only D is still not completely been used. So the pi bond which is formed has to be D pi P pi. Okay, so there is one D pi P pi bond here. It all makes sense. See the next one. Steric number is half of 8 plus 2. You get this as 5, and that will become sp3d. sp3d, but the number of connections you see, 5 orbitals, but only 4 connections, which makes the bond pairs as 1, sorry, bond pairs as 4, and lone pairs as 1. So, which makes it xenon having 3 bonds like this and 2 fluorine here. So, fluorine, now Bent's rule is applicable. Fluorine needs to be kept on the axial direction, and oxygen has to be here. Okay, and one lone pair we have to place it on the equatorial direction as per the Benz rule. This is how it should be. Now notice oxygen is not going to get satisfied with its octet, so we need to place 2 pi bonds also like this. So now it will be completed. Now here is a catch. While writing the bond pairs, right, as per the hybridization, we only write the bond pairs which are sigma bonded, but even a pi bond is also a bond pair, correct? So you will always add the pi bond at the end after the structure is been made. So that means plus 1. So total you will write it as 6 bond pairs. Here also plus 2. You write it as 6 bond pairs. Those 4 are actually sigma bonds. The 2 are pi bonds. Okay. And you can see there are two d pi p pi bonds here. There are two d pi p pi bonds. Got it? And how is the shape look? How does the shape go? Now, what happens here is xenon. If I put the lone pair here for our understanding how the structure looks like, you would actually notice that we will have a fluorine and fluorine here. And on the back side, we'll have one oxygen. On the front side, we'll have one oxygen. So it looks as if it is a seesaw. You know, if I put some kind of a plane here like this, on this plane, you will have this oxygen and oxygen. And these two will be like a seesaw. Okay, it will be like a seesaw. Hence, we can say the shape would be like a seesaw. Okay, expected geometry was trigonal bipyramidal TBP, but the shape is seesaw. All good. Next, notice XeO3. XeO3 H will be half of 8, which is 4, and you can see there are 4 of them, but only 3 connections. So it is supposed to be sp3, and we have xenon with lone pair here with one oxygen, oxygen, and oxygen. So out of the tetrahedral positions, only 3 positions are occupied. One will be lone pair. So you can see the lone pair is 1. Bond pairs. Now I'm counting all of them. How many? 6. 3 sigma and 3 pi bonds. And number of d pi p pi bonds, how many we have? 3 d pi p pi bonds we have here. Okay. What is the shape like? The shape in this case is pyramidal.
How deep I people?
See beta. If you may notice that sp3, S is saturated, P is saturated. That means there is no more S and P orbitals left. Pi bonds are only made by P and D orbitals. So forget about S. P, all three p orbitals are occupied already for hybridization. So for pi bonds, we only require pure orbitals. So where are
Yes.
the pure orbitals left now? Only D, correct?
Yes.
So that's why whatever the pi bond that you're making, that has to be a d pi based. Okay,
Yeah, got it.
please make a note, quick. One second. Yeah. See the next three now. XZF4. H is 4. It is sp3 hybridized. There are 4 orbitals, 4 connections, no lone pairs. So lone pairs are 0. Bond pairs would be 8. Why 8? Because we would have all oxygens with double bond. So this is how the structure would be. So the shape is tetrahedral, tetrahedral, and geometry is also tetrahedral. There are 4 d pi p pi bonds in this case. All okay?
So I had a
Next.
question. If the molecule has a charge on it, do you still count the double bond as a extra bond?
In that case, that charge, if it is negative, would go on to the oxygen, right? And oxygen will be shown only with single bond, not double bonds anymore. Hmm?
Yeah, because in
Like that is the case which we are writing right now. Check out XeO6
yeah.
4 minus. You know? So half into, we have 8 plus 0 minus of minus 4, right? So that makes it 6. So 6 means sp3d2, correct? So based on this idea, we can say there are 6 connections and there are 6 oxygens, right, Vita? So which means the number of lone pairs has to be 0. So there is no lone pairs here, all 6 connections, correct? So which makes it xenon having 6 means we should have octahedral form, right? So it first make it into an octahedral form here. So like this, we have an octahedral geometry with 6 oxygens. And now on this octahedral form, 4 oxygens must have got that minus charge. So minus, 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 and minus. Other two has to be balanced with a double bond only. So this is how the structure has to be. Clear? Now you can see how many bond pairs we have. So number of bond pairs will be how many? 8. Total 8 bond pairs. Because 1, 2, 3, 4 here, 5, 6, 7, 8. Now check one important thing. If I ask you number of lone pairs in the molecule, okay? Because here I was talking only about xenon. What if it was about the entire molecule here? So check out. Here we'll have 2 lone pairs. Here we'll have 3 lone pairs. And same goes with the minus charge carrying oxygens. Here we have 2 lone pairs. So in fact, all the lone pairs will be on the oxygen only. So 1, 2, 3, 4. These 4 has 3 each. That makes it 12. And the other two will have 2 each. So that makes it 4. So total 16 lone pairs we have. All good? Because there are no lone pairs on xenon, geometry and shape both would be same, which is octahedral. Just an octahedral geometry. Next, XeF7 plus. Now, H would be equal to half of, okay, 8 plus 7 minus 1. So that makes it 7. So 7 as in sp3d3. Since it is XZF7, so now it can adapt because there are no lone pairs on the center. So lone pairs are 0, bond pairs are 7. So that makes it now xenon to have that, you know, pentagonal bipyramidal form like this and like this. So this is pentagonal bipyramidal. F, F, F here, F here, F, F, and F, and overall charge is going to be plus here. Now you got to understand one interesting fact here. So, okay, let me rewrite this. So we have F and F here. Wait, okay, sit, wait. So if you have F and F here, check. You know that this is a pentagonal bipyramidal form like this way. This is pentagonal and bipyramidal. Okay, that is in fact the shape. The shape and geometry is pentagonal bipyramidal. Now something interesting here is if I take this bond length, the axial one as x and the equatorial one as y, the bond lengthwise, then normally as per Bend's rule, we have learned that the axial should be long. Here the equatorial will be long because we want equatorials to be as far away as possible just to avoid more repulsions between them. To avoid these repulsions, they'll be as far away as possible, which means they should be as elongated orbitals as possible. So this is also a Bend's rule. And here we always place the lone pairs across the axial and more electronegative across equatorial. Okay. Make a quick note, everybody. If you have a doubt, you can ask me. These we can do it quickly. Check out finding out lone pair, bond pair, shape of the following. Okay. We'll do it jaldi. Check. Hybridization is 3, which makes it sp2. Okay. So bond pairs are 6, lone pairs on sulfur are 0. Total lone pairs because they are only present on oxygen will be 6. The structure is like this: S double bond O, double bond O, and double bond O. So two lone pairs here, two lone pairs here, and two lone pairs here. This is the structure. Okay. Shape is trigonal planar. Trigonal planar. H2SO4 steric number is 4. It is sp3. Got it? So check out the shape: S double bond O, O and H here, O and H here, double bond O here. Okay. So bond pairs, if you count all the bond pairs, there are 8. Lone pairs, 0 on sulfur. Total lone pairs, each oxygen will have 2, 2. So 4 2s are 8. These are the total lone pairs. Okay. Shape wise, it is tetrahedral. Next, H2SO5. Okay. Now, this is more structure based, everybody. So, for S2SO5, you need to know the structure prior. How you know? Sulfur has double bond O, double bond O, and here uh, oxygen is bonded with hydrogen, but the other side there are two oxygens back to back connected like this and H. Okay, so this is called peroxysulfuric acid. Peroxysulfuric acid. Okay, check number of bond pairs here. So we have this as 4, 5, 6, 7, 8, 9. So total we have 9 bonds. Lone pairs on sulfur is 0. Okay. Geometry with respect, the shape with respect to sulfur, is still tetrahedral. It is tetrahedral. Okay, please check quickly. Done. See the next one. SO2, SF4, SF6. Steric number is 3. sp2. Only two connections, but one which makes it one lone pair on sulfur. So sulfur must have one lone pair. Okay. And if you notice the bond pairs will be four of it. So that is sulfur having one lone pair, and then other two connections are with oxygen. So that leads to formation like a bent V shape. So you can see it is like a bent V shape. So the shape in this case is bent V, bent V. And you can see uh, sulfur has one lone pair, and total number of lone pairs, if you compare, every oxygen will also have two each. So total we have five lone pairs on this case. Clear? Check. Check next one, SF4. So in the case of SF4 here, steric number is 5, which makes it sp3d. So it is sp3d. Lone pairs are 1. So we came across this. This is going to be the seesaw shape one. So I'm directly writing the shape. Lone pair here, one fluorine here, and one fluorine here. Now notice this one. I'll be using this representation. One fluorine like this, and one fluorine like this. So this is called a solid wedge. Solid wedge means it is coming out of the plane. It is coming out of the plane. And if I write like this is called dash wedge. Dash wedge means it is going inside the plane. So you can see this fluorine is going inside, this fluorine is coming outside, and these two are on the plane. So if I keep everything on a line, that means it is on the plane. This is a standard representation. Okay. So bond pairs, how many we have? Four bond pairs we have. Total lone pairs. Let me write total lone pairs. total lone pairs will be equal to each fluorine will have 3. So 4 3 is 12, 12 plus 1, 13. So 13 we will have. Okay.
Could you repeat the shape?
Seesaw. Seesaw shape. If you're not able to visualize, let me show it to you. How it appears. Okay. So you can see these two, the yellow one, the yellow marker is coming towards you. The pink marker is coming towards me. Correct. And then we have these two black pins here, like this. Got it? So if I
Yeah.
keep it, this is a seesaw. Clear?
Okay.
Yes, Kapil. Doubt?
Yeah, I got it.
Yeah.
So can you explain why is it like that out of the plane and inside the plane? Two of the fluorine.
See, the geometry what we were expecting was what, beta? It is supposed to be like this. Penta, triagonal, bipyramidal. Correct? This is how it is supposed to be originally. But what happened? Now this got occupied by lone pair. And because of this lone pair, it will start repelling it here, because of which now it starts showing some bend. Okay. So that means these two lines will start showing some bend here, like this. Clear? Now I know that these three are on one plane. These three. This is all in one plane. Correct? But you know that this is coming out of the plane and this is going inside the plane. That's how you can make trigonal bipyramidal. Correct? So it is basically coming out of the plane, this line, and this line is going inside the plane, like this. Barabar? So let me copy that again here. So this is how it is, beta. Okay. Now all I did, Dev, is turn it around like this. That's it. Clear?
So can you
This is
explain the
making
last
sense?
part once again? Just after it
See.
started bending.
So after it started bending, this is how it was, right? Hmm? Just while writing the structure, I turned it around and wrote it. That's it. So that the lone pair is appearing up. Okay. ऐसे समझो कि this is a ground. ये ground है जिसके ऊपर these two are fixed. These two positions are fixed. Okay. And imagine two kids sitting on this position. So how does it appear?
Like a seesaw.
Like a seesaw. Yeah.
Yeah, got it.
So to explain that structure, I took this and rotated around. That's it, like this. Okay. Clear?
Yeah, sir.
Right. Now let's see SF6. One second. Next. SF6, H is 6 here and it is sp3d2. So lone pairs on sulfur are 0. Bond pairs are 6, which makes sulfur to have 6 connections this way. 6 fluorides here. And that's it. So this is a perfectly octahedral form. So there is no distortion here. So total lone pairs. So you can have total lone pairs here. Each fluorine will have 3. So 6 3 is 18. So this will be the total number of lone pairs. Next, SOCl2. SOCl2 steric number is, 6 plus 2. This will be 4, which makes it sp3. So it is sp3. Lone pairs, you can see there is one lone pair which can be accommodated. Bond pairs, oxygen will make two, chlorine will make two, so that makes it four. So it is like sulfur having one lone pair here, one double bond O here, chlorine here, and chlorine here. So it will be like a pyramidal shape, right? So the shape is pyramidal. Okay. Total lone pairs, if you notice, total lone pairs. Two chlorines will give three each, so that makes it six. Oxygen is making two, sulfur is making one. So total nine lone pairs. Okay. Next, SO2Cl2. Steric number is, again 4, which makes it sp3. This time there is no lone pairs on sulfur. So lone pairs for sulfur is 0. Bond pairs we got it as 6. That is, here that same lone pair position has been now occupied by oxygen. So that makes it total lone pairs as 6 plus 4, 10. Okay. And shape is perfectly tetrahedral form. So it is a tetrahedral structure. Next, SCl2. SCl2 steric number is 4 again. It is sp3. So lone pairs on sulfur will be 2. Bond pairs will be 2. Just like water. This is similar to water. So we have two lone pairs and two chlorines here. So the shape now would be only about this bent V shape. That is how this will be. So it is like bent V shape. And total lone pairs will be equal to, both chlorines will make it 6, and this is 7 and 8. So total lone pairs are 8. So please check this out quickly. If you have a doubt, you can ask me again. You need to know the structure. So these are cases where we need to know the structure. K2Cr2O7. First, I'll write the structure, then you decide what is the hybridization. Okay. So, for example, I have chromium with oxygen, chromium, double bond O, double bond O. Then we have minus, double bond O, double bond O. Then we have minus with K plus and K plus. This is the structure of K2Cr2O7, KMnO4. Mn, double bond O, double bond O, double bond O, and O minus and K plus. This is KMnO4. Cl2O7, same as the above. Cl, O, Cl, double bond O, double bond O, and double bond O, double bond O, double bond O, and double bond O. Next, Al2Cl6. Okay. So Al and Al will have Cl, Cl here, Cl, Cl here, and Cl, Cl here. This is how it is connected. Like this. This is Al2Cl6. Thiosulfate. We have sulfur connected to another sulfur. We can have this as O minus, O minus, and double bond O. This is thiosulfate. Tetrathionate. One second. We'll have O, O, and S here. Sorry. We have S, S, and S here. Then we have double bond O here. And then at the ends, we have O minus, like this. So here we have lone pairs, this way. Okay. So guys, please check the structures, whatever I have written. Try to identify the hybridization of the one which I'm marking right now. Okay. Hybridization of chromium, and this oxygen. Similarly, manganese here, chlorine, and this oxygen, aluminium here, and sulfur here, and this sulfur also. And about these 4 sulfurs, what is the hybridization? Chalo, do this now. I have given you the structure already. Now, based on the number of sigma bonds, only count the sigma bonds. Based on sigma bonds, try to predict what would be the hybridization? Try it out. So we'll start with the first one. What did you get the first one? There are four connections, make it sp3. Same goes with sp3. Now have you noticed something? This oxygen has two lone pairs and two bonds. Two lone pairs and two bonds will also make it as sp3 only. So even the oxygen is sp3 hybridized. MnO4 is also like four sigma bonds, which makes it sp3. Don't count the pi bonds, okay? Only count the sigma bonds. Here also, there will be two lone pairs on oxygen, which makes it sp3. And these two chlorines will make it sp3. Next, aluminium also here, four connections that makes it sp3. Okay. Chlorine also, I'll just mark for chlorine also. Chlorine will have two lone pairs and two bond pairs, so that will also make it as sp3. Here, chlorine is actually making a dative bond, because of which it will have only two lone pairs, not three lone pairs. One lone pair is involved in the uh, dative bond, so it is sp3. Here, this sulfur has four sigma bonds, make it sp3. And notice this sulfur also. This sulfur will have sorry, two lone pairs. Two lone pairs here. Yeah, only two lone pairs. Sorry. So two lone pairs and one sigma bond. Two lone pairs and one sigma bond makes it sp2. So one sulfur is sp3, one sulfur is sp2. S4O6 2 minus. So uh, here we have four connections. So that makes it sp3. Here also four connections makes it sp3. Now both of these will also have similar thing. Two lone pairs, two sigma bonds. So makes it sp3. So all of these are sp3. Okay. So you can see majority of them are sp3 only. Check out properly. Any doubt? Done. Shall I go ahead? Next. Notice this. When it comes to organic compounds, right? So first we need to check out what type of molecule are we talking about. Okay. So for example, if you notice, we have alkyne, alkenes, and alkanes. The ratio of carbon and hydrogen would be like this, where we have uh, for every n number of carbons, we will have 2n minus 2 hydrogens. Okay, got it? Check. So alkynes, alkenes, and alkenes. Now, when you say alkynes, we expect it between carbon and carbon there is a triple bond. Alkenes will have double bond. Carbon carbon will have a single bond when it is alkenes. How do we decide on the hybridization? Simple. Again, check out the number of sigma and pi bonds. This carbon has two sigma bonds. One is on the left, one is on the right. So two sigma bonds will automatically imply that it is sp hybridized. Same is the case with this one also. It has two sigma bonds that makes it sp hybridized. Here, this carbon has two hydrogens. See, this way of writing is called as compact way or condensed way of writing the molecule. Here, basically, it meant that we have two hydrogens connected to carbon and then another two hydrogens connected to this carbon. So, in short, this carbon has three sigma bonds. So, that means three sigma bonds implies we can make a hybridization of sp2. Same is the case here. 3 sigma implies that we have sp2 hybridization. While here we have 4 sigma bonds, which makes it as sp3. Same goes with this one. 4 sigma makes it sp3. Got it? So all you need to find out is how many single bonds, double bonds a carbon will have. Single, double, and triple bonds it has. Okay. And there are few important functional groups of organic compounds like alcohol, aldehydes, carboxylic acids. Alcohols means typically like this. If you have CH3, CH2, OH, this is ethanol. Basically, here carbons are like this connected. All of them are connected like this. Oxygen has two lone pairs on it. So you can see if you check out the hybridization of carbons and oxygens. So these two carbons have four connections each. This one also has four connections. Oxygen also have two connections and two lone pairs. So that clearly makes this as sp3, this as sp3, and this as sp3. So if the group here, the connected oxygen OH here, right, is connected, then that is called alcohol. Okay. So in this particular alcohol, we have carbon as sp3. This carbon also has sp3. Next, aldehyde, CH3, CH3, CHO. So where we have three hydrogens connected with C, double bond O and H. This is how the connection is. So in that case, now I can say this carbon, oxygen and carbon. If you compare, this is sp2. This is this is no hybridization, and this has sp3. This is sp3 form. Next one is carboxylic acid, something like CH3COOH. This is a general form of writing carboxylic acid, which is carbon having three hydrogens on it, and next carbon having double bond O connected to O and then H. So here again, if you check this carbon, and this oxygen, hybridization is sp3, and here it is sp2, and here also it is sp3. Okay, so please check how we have written these cases.
Sir,
Yes, beta.
in carboxylic acid, won't carbon have a lone pair?
Carbon, no, beta. Carbon does not have any lone pair. Hmm? Clear? All done? Sure. Next, let's see what is this borderline structures means. Okay. See, bond line structures. Bond line structures is basically we have any carbon, right? I mean, we have, let's say, uh, carbons connected with lot of carbons and oxygens, maybe another carbon somewhere. Then we have nitrogen here, like this. And rest all are hydrogens, imagine. This is how all the connections are being. Okay. This is a complete structure showing all the bonds on carbon and oxygen here. Got it? Now, for this molecule, if we do like this, see, I take this, every carbon has one dot. Okay. Every carbon has one dot forms. Okay. So, like this, I'll take one dot here and another dot here, another dot here. And then there is an oxygen somewhere in between. And then that oxygen is connected to another dot. And then we have nitrogen here, like this. So, put it in a zigzag way, like this. Okay. And then connect them, connect all of them like this. So here, here, like this, like this, like this. Okay, you connect this. Only show the hydrogens which are there other than carbon. Other than carbon, this you can see nitrogen. Sorry, nitrogen cannot have this many bonds. It will have a lone pair. Okay, same is the case here. So nitrogen has two hydrogens. So only show that on nitrogen. Do not show it on carbon. Correct? So this structure is called as the bond line structure of the given molecule. This is the bond line structure. Clear? Let me show one more example. Suppose I have like this. I have carbon, then I have a triple bond, then I have another carbon, then I have a double bond here like this. Then I have oxygen, then I have a carbon, then I have a double bond here with nitrogen, and then I have a connection with hydrogen like this. Let's say this is how I have all the bonds given. If you have to write the bond line structure here, correct? So there are two ways we can write, especially at the case of where you have a triple bond. At the triple bond, there are two ways to write. I'll show you first. First, you can write those dots here. So let me show with the dots. A dot, a dot, and a dot, and dot. Four dots, five dots. Okay, sorry, six dots. And then we have oxygen, then we have another carbon, then nitrogen. Okay. So where are the oxygens? First, let me keep connecting and check out. 1, 2, 3, 4. So I'll write the numbers also. 1, 2, 3, 4, 5, 6, 7, 8, 9 positions. So 1, 2, 3, 4, 5, 6, and seventh position was oxygen. Correct? So for oxygen, we cannot write the dot. So only oxygen. And then last one we have nitrogen. So we have oxygen here, then connection here, and then to nitrogen. Okay. So this is the way we'll write down first. And then now try to represent the bonds which are other than single bonds, right? So here between 2 and 3, we have a triple bond. So I can write it this way. And between 5 and 6, I have a double bond. I can write it this way. And between these two, again, I have a double bond. I can write it this way. That's it. Okay. And now nitrogen has one hydrogen. So I have to represent that. This. Okay. So this is the form that we have to write down. Okay. So this is the bond line form. So one rule we will learn that in organic chemistry more, more importantly and more strictly we will follow that in organic chemistry. That is whenever there is a triple bond, instead of writing in a zigzag way here, we actually write in linear way. Like this is 1 and this is 4. This is second, this is third. So between these two, we'll simply write these two lines, and here we'll represent it as a single line only like this. This one. Okay. So wherever you have a triple bond, this is to be adapted like this. Clear? But that is not very strictly followed. Like I said, in organic chemistry, when you have been given the compounds, then only you will check it out. And now, guys, suppose if you have, if I ask you what is the hybridization, let's quickly analyze this hybridization form for this carbon, this carbon, this one, this one, this one, this one, and this one. So check out what is the hybridization in all these cases. So starting with this, four connections, four single connections, sp2, only two sigma bonds, sp, sp, sp3, sp2, sp, sp2, and sp2 again. Okay, sorry, here I put one extra hydrogen. There is no extra hydrogen here. Okay, because carbon can maximum has only four bonds. So these are the number of bonds we have. Please check any doubt you have. You can ask me now. Now I'll give you the structure. I want you to figure out what is the hybridization of every carbon and also how many hydrogens each carbon will have it. Okay, so I'll give you bond line structures. Check it out. First one, check out bond line structure. First case, same way. Check out the second case here. Right. Check out for these cases. First, figure out how many hydrogens it can have. For these cases, just mention how many hydrogens we have, and then mention what are the hybridizations on each of them. Okay. So in the first case, check out at every carbon. What I'll do, this carbon here, here, and here, 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 and here. At all these positions, what is the hybridization? Quickly check it out. So first case, if it is only single bond, so it is all sp3. sp3. There is a double bond coming means it is sp2. sp2. This is also sp2. sp2. This is sp3. sp3 because that is all single bonds. Okay. Now, if at all I have to represent the number of hydrogens on it, I can maximum make 4 connections, right? So you can see this carbon has 1 connection, so that means other 3 has to be hydrogens. Here, other 3 has to be hydrogens. Here there is 1 hydrogen. 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 Here this carbon has 3 hydrogens. Here this carbon has 3 hydrogens. So please check this out. This is how I'm asking you to check out how many hydrogens are connected. Guys, do this work here only so that you feel comfortable in organic chemistry. Okay, this is all organic chemistry part. If you learn it properly here, it makes it very easy for you to understand structures, write their diagrams, okay, realize their hybridization, planarity, everything. Do the same thing for the second case quickly. Let's see. So first, let me figure out what is the hybridization here. Okay. So in all these cases, since we have all the single bonds here, majority of them are sp3. These two are not. So putting with that, so you can see first we have sp, sp, sp3, 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 and sp3. And now let me put down all of those cases, how they are connected with hydrogens. So 1, 2, 3. 1, 2, 1, 2, 3. 1, 1, 1, 2, 3. 1, 2, 1. That's it. These are the number of connections. Just count the number of red arrows, red lines which I used. 3, 3, 3, 9, 10, 11, 12, 13, 14, 15, 16. So yes, 16 hydrogens we have. Clear? Do the next one. Please check how much you're getting. So first let me put the hybridizations in all the positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all the places where I need to figure out hybridization. So check, this is sp3, 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 and sp3. sp2, this is sp2 and sp2, and this one is also sp3. Okay. Now let me put all the hydrogens. Here we must have 3 connections. The terminals will always have 3 connections. Center will have 2. And if 3 connections are already there, one more connection. Here also 3 connections already there, one more. Here we'll have 2. Okay, I'll not write the hydrogen. You should understand that. Here we have two, here we have two, here we have only one and one. Okay, so these are the number of hydrogens. So let's count here. So across the ring we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 9 plus 6. Okay, 15, 16, 17, 18. So we have 18 hydrogens here. Can I do it for the last structure quickly? 3 here, 2 here, 2 here, 1 and 1 here, 1 and 1 here, 2 here, 1 here, 1 here, 2, 2, 1 and 1. Okay. So let's count it now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Can you please check? Did you miss anything? Vidya, you got them all now? Oh, sorry. I forgot one more also. Here there is one more. 21, 22. Please check now. Did you get it? Everybody clear? Right.
Yes, sir.
Done. Okay. So this is the next task I would want you guys to do. That is, figure out how many p pi, p pi, p pi, d pi bonds are there in the following here. Okay. In the notes, if you have taken the printout, you must have seen I have given enough gap for solving that. So please finish this part at least, guys. Okay. It's not big a deal. You should be able to do it now. We have done thoroughly uh, all these cases. So next class I'll discuss everything about the Benz rule, right? Draco's rule, bond parameters, okay, MOT, molecular orbital theory, correct? Up to this we will finish this off, up to molecular orbital theory. And then we can have the applications of dipole moment. So I kind of require one and a half classes more to finish this. Clear?